Was I not? Yeah, I was muted. Okay. So we're doing this multiplied by constants. We can do a combination of left shifts and additions. We first consider the case of multiplying by a power of 2, and then we generalize this to arbitrary constants. A principal multiplication by a power of 2, let x be the unsigned integer representing by bit pattern so and so. Then for any k, with w plus k bit unsigned representation, blah blah blah. So for example, 11 can be represented for w4 as 1011. Shifting this left by k2 yields 6-bit vector, which encodes the unsigned number 11 times 4. So just shift left. We're doing powers of 2. Okay, unsigned multiplication by powers of 2 for C variables, unsigned values, blah blah. Yep, same statement. Practice problem. Oh, there's another principle here. That was a derivation. Principle 2 is complement multiplication by power of 2. Note that multiplying by power of 2 can cause overflow with either unsigned or 2's complement arithmetic. Our result shows that even when we will get the same effect by shifting. Returning to our earlier example, we shifted the 4-bit pattern left by 2 positions to get, so it's a 44 truncated to 4-bit skews. 44 mod 16 or 12, given that integer multiplication is more costly than shifting and adding. Many C compilers try to remove many cases where an integer is being multiplied by a constant with combinations of shifting, adding, and subtracting. For example, suppose a program contains the expression x times 14, recognizing that 14 is equal to 2 to the power 3 plus 2 to the power 2 plus 2 to the power 1. The compiler can rewrite the multiplication as x left shift 3 plus x left shift 2 plus x left shift 1. Replacing one multiplication with 3 shifts and 2 additions. The 2 computations will yield the same result regardless of whether x is unsigned or 2's complement. And even if the multiplication would cause overflow, even better, the compiler can also use the property 14 is equal to the 4 minus 2 to the 1 to rewrite the multiplication as x bit shift over 4 minus x bit shift over 1, requiring only 2 shifts and a subtraction. Alright, so we got practice problems here. Two dot 38 dot. As we'll see in chapter 3, the LEA instruction can perform computations of the form A bit shift over K plus B. This is load effective address. Where K is either 0, 1, 2, or 3, and B is either 0 or some program value. The compiler often uses this instruction to perform multiplications by constant factors. For example, we can compute 3 times A as A bit shift over by 1, which would be 2 times it, plus A. Considering cases where B is either 0 or equal to A, and all possible values of K, what multiples can be computed with a single LEA instruction. well, you'll have the term here. So b is 0 equal to a itself. What multiples of a can be computed with a single LEA instruction? It's going to be limited by the bit width. And there's no bit width specified in the problem. Bit width (238). Chapter 3 will see many examples of LEA instruction in action. Instruction is provided to support point arithmetic, but the C compiler often uses it in a way to perform multiplication by small constants. For each value k, we compute two multiples, k 2 to the k where b is 0, and 2 to the k plus 1 where when b is a. Thus we can compute 1, 2, 3, 4, 5, 8, and 9. Plus 38, 239. Let's continue reading. Generalizing from our example, consider the task of generating code for the expression x times k for some constant k. The compiler can express the binary representation of k as an alternating sequence of zeros and ones. This stuff I'm not interested in at all. Okay, for example, 14 can be written as so-and-so. Consider a run of ones from bit position n down to bit position m. For case of 14, we have n is equal to 3 and m is equal to 1. Compute the effect of these bits on the product using either of two forms. By adding together the results of each run, we are able to compute x times k without any multiplications, of course. The trade-off between using combinations of shifting and adding and subtracting versus a single multiplication instruction depends on the relative speed of these instructions, and these can be highly machine dependent. Most compilers only perform this optimization when a small number of shifts, adds, and subtractions suffice. I think I should highlight the LEA, use of LEA. How could we modify the expression for form B for the case where bit position n is the most significant bit? I don't care. For each of the following values k, find ways to express x times k using only the specified number of operations where we consider both additions and subtractions. If you have comparable costs, you may need to use some tricks beyond the simple form A and B rules you have considered so far. I don't care. For a run of ones starting at bit position n down to bit position m, n greater than m, we saw that you can generate two forms of code A and B. How should the compiler decide which one to use? So it's going to be 239, 240, 241, 9, 240, 241, and I'll go to readme. Say skip here. Okay, divided by powers of 2, integer division on most machines is even slower than integer multiplication, requiring 30 more clock cycles. Divided by power of 2 can also be performed by a right shift, arithmetic right shift. You use shift operations, but we use the right shift rather than left shift. The two different right shifts, logical and arithmetic, serves this purpose for unsigned and two's complement numbers, respectively. Dividing unsigned numbers by a power of 2. This example illustrates how performing logical right shift by k has the same effect as dividing by 2 to the k, and then rounding towards 0. Integer division always rounds towards 0. To define this precisely, let's introduce some notation. For any real number a, define a to be the unique integer a prime, such that a prime is less than or equal to a, which is less than or equal to a prime plus 1. This example is 3.14. Yeah. And so we define a with a little hat on it, or what do you call those? A in its house to be unique integer a prime, such a prime. Okay. Floor, that's a floor operator. It should round down a positive result, but round up a negative one. Okay. The case for using shifts when unsigned or arithmetic is straightforward, in part because right shifting is guaranteed to be performed logically for unsigned values. Okay, we're almost done here. Okay, unsigned division by power of 2 for C variables x and k with unsigned values x and k, such as 0 is less than or equal k is less than or equal w. The C expression x to k, right shift k, yields the value x divided by 2 to the power of k. As examples, figure 2.28 shows the effects of performing logical right shifts on a 16-bit representation of 1, 2, 3, 4, 0 to perform division by 1, 2, 16, and 256. The zeros shifted in the form the left. Sorry, the zeros shifted in from the left are shown in italics. We also show the result of we would obtain if we did these divisions with real arithmetic. These examples show that the result of shifting consistently rounds towards 0, as it is convention for integer division. All right, let's take a look at it. What's k? Applying arithmetic right shift, the examples illustrate, okay, k is in the table there. Okay, so you got decimal representation, and we say k is shift, then we get the numeric representation. Same thing here. How is that correct? Oh, 2 to the k, so we divide by 1 basically. But it was bit shifted. To the 1, it would be divided by 2. Wait a minute here. What's going on there? That's a weird one. So you have this bit representation. How many bits are there? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. So it's a 2-byte sequence. That's what it looked like. It's a short. Oh, I see what happened there. So we did the right shift. It represented it as division by 2. And then we say, okay, what if you divide this thing by 2? Okay, I see what they're doing. Wow, it took me too long to get that. All right, so 4 would be 2 right shifts. Yep. Oh, and the K is 4, so it's going to be 4 right shifts. Okay. And then 8 as well. Okay. And because it rounds to 0, it goes to 49. No. Rounds down. Okay. Let's go back here. Let X be the unsigned integer representation by bit pattern so-and-so and K be so-and-so. This bit vector has numeric value x prime, which we have seen is the value that would result by computing the expression so-and-so. Two's complement division by a power of 2 rounding down. I forgot to add some food to my macro tracker. Final thoughts on integer arithmetic. Sorry, I'm just reading to myself here because, well, it's working for me. As you've seen, the integer arithmetic performed by computers is really a form of modular arithmetic. The finite word size used to represent numbers limits the range of possible values, and the resulting operations can overflow. We have also seen that the 2's complement representation provides a clear way to represent both negative and positive values while using the same bit level implementations as are used to perform unsigned arithmetic. Operations such as addition, subtraction, multiplication, and even division have either identical or very similar bit level behaviors, whether the operands are in unsigned or 2's complement form. We've seen that some of the conventions in the C language can yield some surprising results, and these can be sources of bugs that are hard to recognize or understand. We have especially seen that the unsigned data type, while conceptually straightforward, can lead to behaviors that even experienced programs do not expect. We have also seen that this data type can arise in unexpected ways, for example, when writing integer constants and when invoking library routines. Assuming data type int is 32-bit long and uses 2's complement representation for signed values, right shifts. I think I did this. This is part of the lecture, so I'll go ahead and do these. 2.44. So assume int is 32 bits long. Sorry. Int is 32 bits. And uses 2's complement representation. 2's complement. For signed values, right shifts are performed arithmetically for signed values and logically for unsigned values. The variables are declared and initialized as follows. So we have int x is equal to foo, int y is equal to bar, and then we got unsigned ux is equal to x, and unsigned uy is equal to y. Okay. Then for each of the following C expressions, either 1, argue that it's true, evaluates to 1 for all values of x and y, or 2, give values of x and y for which it is false, so some type of counter example. So A, x is greater than 0. Or x minus 1 is less than 0. So it's just for a signed value. We could say x is greater than 0, or x, which is negative, minus 1 is less than 0. Not true, because t min, we'll say not true, because t min minus 1 will be positive. B. Okay, we got x ampersand 7 is not equal to 7. So we got some bits in there that weren't set. So this means that we got bits, the low order 3 bits that represent 7 are not all set. One of them set to 0. Not equal to 7, or if they are all set to 0, or sorry, set to 1, then if we bit shift over 29, yeah, that'll be less than 1, true. So it says each of the following, either argue that it's true, evaluates to 1, or give values. So true, If x ampersand 7 is equal to 7, then all ones are set in low order bits, then shifted up to the sign bit location. See, x times x is greater than or equal to 0. So that would be true for normal values of x, but we say false. Say false here. If we just do a clang REPL here, and we do pound include standard io.h printf %d, new line, we'll say int 32t I need to include, I think it's standard int. There we go. So int 32t of, we'll just make sure these get applied correctly here. So it's going to be what? 32, which would be the most negative value, would be 0x80. That's 1 byte, 2 byte, 3 byte, 4 byte times, oops, god damn it. Okay, let's try this again. 0x80. It's 1 byte, 2 byte, 3 byte, 4 byte. How is that oh, because I don't have a value here. There we go. It overflowed. Okay, great. The compiler detected it. But what we wanted to demonstrate is that it might, times itself might be not negative, or might be negative. Let's just try it. 0. We'll just say x here, and then we just say x times x. Yeah, we'll do that. That'll simplify things. X times x, and here we say int 32t is equal to x is equal to 0x80, 1, 2, 3, 4. And then we do this. Really? And if we do like 1, 2, 3, 4. Oh, now I don't have to declare the type. Come on, stop doing that. There we go. Well, let's do 8. Eight 00F 00F. So that'd be 1, 2, 2, 3, 4. About to overflow. We just got to get a little bit higher. Maybe throw an F here. There we go. So that's a negative times a negative. Because if I print out just x, it's also negative, and it gives you a negative. So I'll just grab this value, and that'll be our counter example. False. A negative value multiplied by itself can overflow and still be negative. E.g., yeah, D. So x is less than 0, okay, so negative value, or negative x is less than or equal to 0. So either that's true, or in the case where it's not true, x is either equal to 0 or x is greater. Yeah, that's true. Oh, these aren't positive. Sorry. I misunderstood that one. So either x is... Wait a minute. I did understand that one right. E is the one that I was looking at. So now x is greater than... So let's look at D again. X is less than 0. So it's negative. Or it's positive or 0. In which case, 0 case, it'll work out. In any positive case, negating it will be less than 0. Yep. Now, when x is greater than 0, when we negate it, we'll say no, false, because t-min negated will be itself. F, x plus y is equal to uy plus ux. True for all cases. Let's see. Seems like it's something that should be true. So let's just think through this. So say x and y are both t-min, then they're going to overflow. Well, let's just take the example, x is t-min and y is 0. So that's going to be t-min on the left. And then over here, our unsigned x I think it's true. Yep. True. Because summation for both unsigned and 2's complement values are the same, and equals, yeah, we'll just say the same, and equals converts the left hand side to unsigned G. Okay, it's a different equation here. So you got x times negation of y plus uy times ux is equal to negative. Ooh, yeah, that's quite the expression. Let's try to break it down. So we have two terms being added together. This one, x times its negation. So you could be overflowing there. It's commutative, so we can swap those ux times its original. Guess is true, but I have no idea. Okay, we're done with this part of the chapter. Let's check our answers. 244. Boop, boop, boop. 244. These C puzzle problems provide clear demonstration that programmers must understand the properties of computer arithmetic. So the first one is false. Yep. Second one is true. This one is false. C. D is true. E is false. F is true. And then G is true. Should put a comma here to be consistent. True. Let's see. Y equal tilde equals negative y minus 1. Ux equals x times y. Thus, the left-hand side is equivalent to all that. Okay, whatever. So negation of y. I guess you could always say the negation of any 2's complement value would be its value minus 1. Yeah, the negation of the value. The inverting of the bits is equal to the negation of the value minus 1. Yeah, that's true. So if we go back to the problem, so that's going to be x times negative y minus 1. Ux times uy equals x times y. Oh, I see, because it has to be distributed. Okay. Floating point, baby. We're here, finally. How many pages we got on floating point? About 18. Do I want to do the reading of the lecture? Kind of want to do the lecture and then go to bed, because getting through this floating point stuff, I guess there's a lot of diagrams which are nice. I don't really feel up for it right now. It's getting late, so let's watch a lecture on floating point. So let's go over to here. It's on my GitHub, and we'll go here. And we're going to go, where's lectures here? Video lectures. Lecture 4 on floating points. README. Lecture 4, so I'll complete this tonight. Oops. Come on. Okay, so we did some lectures, we did some problems. Oops. Left some things there that I need to fix. Vim chapter 02 problems. And I want to search for, actually it'd be this. Yeah, here. There we go. Oh, we got a new lecture. That's nice.
Good afternoon, everybody. Welcome. It's good to see you. So today we're going to study a arcane area of computer systems.
I'm gonna go get something to drink real quick, and I'll be back to watch this lecture.
So today we're going to study a arcane area of systems known as floating point, which is the way that computer systems represent the real numbers. So you're all familiar with decimals, something like 3.14, and there's a similar idea with binary numbers. Okay, so what does a fractional binary number like 1011.101 represent, and how does that work? Well, it works just like the fractional decimal numbers that you're used to. So you have in this case, it's a binary point, and to the left of the binary point, you have bit positions representing powers of 2, so 2 to the 0, 2 to the 1, 2 to the 2, so 1/2, 1, 2, 4, and so on. And to the right of the binary point, you have 2 to the -1, 1/2, 2 to the -2, 1/4, 2 to the -3, 1/8, and so on. And so we can represent any fractional binary number using this notation, where we sum the bit at position k times 2 to the k. Okay, so it really works exactly the same way as with base 10, just with base 2. So let's look at some of these values. So 5 3/4 we would represent as 101.11. So this is before plus 1 is 5, plus 1/2 plus 1/4. Okay, so 2/4 plus 1/4 is 3/4, so 5 3/4. Okay, so that's pretty simple. 2 7/8 is 10.111. So that 10 is 2, of course. And then 0.111 is 1/2. So 4/8 plus 1/4 is 2/8 plus 1/8. Okay, so 7/8. And 1 7/16 would be 1.0111. So that the 1 to the left of the binary point is 1. And then we have 1/4 plus 1/8 plus 1/16. So 1/4 is 4/16. 1/8 is 2/16, and 1/16. So you add those up, you get 7/16. Okay, now notice for some of these numbers, this bit pattern 101.11, if we shift it to the right to get 10.111, we've divided by 2, right? So we've taken 5 3/4 and divided it by 2. And it works the other way too. If you shift to the left, you multiply. If you shift to the left by 1, you multiply by 1. And these numbers that are all 1s to the right of the binary point these are numbers that are just slightly less than 1. Okay. And so when we want to represent those, we'll often we'll sometimes refer to those numbers of that form as 1 minus epsilon, and epsilon just depends on how many bits you have to the right of the binary point. So epsilon gets smaller the more of those bits you have, or it gets closer to 1, and epsilon gets smaller the more of those bits you have. Now there's limitations in this kind of representation. So first of all, we can only represent rational numbers of the form x by 2 to the k.
It's the same problem with decimal, like fractional decimal values. Sometimes you get repeating strings. You can't represent every value.
Exactly. Other numbers have to have repeating bit representations that can't be represented with a finite number of bits that we have in a computer system. So for example, things like 1/3 is this repeating representation. 1/5 and 1/10 are other examples of that. Now the other problem we have is that we can only there's only so many bits to the left and the right of the binary point. So we're kind of if we move the binary point to the left, then we don't have as many. We can't represent as many large numbers. We can only represent small numbers, but we have more precision to the right of the binary point. Right? So we can represent more fractional values. Just the range of those values will be much smaller. Similarly, if we move the binary point to the right, we'll have a larger range of values, but we won't be able to represent as many fractions. Okay. So there's this kind of trade-off, and floating point is a representation that enables us to move that, basically to move that binary point to represent sort of as wide a range as possible with as much precision, given the number of bits, the finite number of bits that we have to work with. So the float and floating point is this sort of shifting binary point, right? This floating binary point. Now, up until 1985, floating point was just a disaster. And every computer manufacturer had their own representation. You couldn't, and it was just terrible because you couldn't predict what would happen if you moved your program from one machine to another. The behavior would be different, the rounding would be different. It was a very difficult situation, and people really, computer scientists in particular, really disliked floating point. In 1985, IEEE, which is the Professional Association for Electrical Engineers, introduced and it's also a very important standards body. They introduced a standard floating point representation called IEEE floating point, which was then adopted by all computer manufacturers. So now the situation, they introduced a standard floating point representation. Floating point, which was then adopted by all computer manufacturers. So now the situation's much better. Everybody supports the same kind of floating point representation. which is what we're going to learn about today. So the floating point has the form, it represents numbers in this is like a scientific notation. It represents numbers of the form -1 to the s, where s is a sign bit, times a significant m, okay, times 2 to some exponent e. Okay, so all of the numbers that we can represent in floating point have to be represented in this form. So the sign bit s determines whether the number is negative or positive, obviously. The significant m, so this is sometimes called a mantissa, which is where the m comes from. The significant m normally is a fractional value in the range between 1 and 2. And we'll see why that is in a second. And then the exponent e weights the value by some power of 2. Okay, so this is encoded in either 32 bits or 64 bits in the following way. The sign bit s is the most significant bit.
I'm going to restart this because it seems like the video is out of sync with the
Good afternoon,
slides.
everybody. Welcome. Much better. Everybody supports the same kind of floating point representation, which is what we're going to learn about today. Significant bit, the most bit s, the sign bit in either 32 bits or 64 bits in the following way. The sign bit s is the most significant bit, and then this is followed by some number of by some number of bits called the exp field, which encodes the exponent e, but it's not identical to e. It encodes e, and we'll see how that works. And then and then that's followed. The remaining bits are the frac field, which encodes m but isn't identical to m. Now IEEE floating point provides two different kinds of floating point. There's single precision, 32 bits, and so-called double precision, which is 64. There's this funky Intel extended precision, which is non-standard, and we won't talk about it anymore. And so in the single precision, 32 bits, you have one sign bit. There's always a sign bit. You have 8 exp bits, and you have 23 frac bits. In double precision, you have 11 exp bits and 52 frac bits. Now, there's a number of different kinds of floating point representations. The sign bit, the extended precision, which is non-standard, and we won't talk about it anymore. And so in the single precision, 32 bits, you have one sign bit. There's always a sign bit. You have 8 exp bits, and you have 23 frac bits. In double precision, you have 11 exp bits and one sign bit. There's always a sign bit. You have 8 exp bits, and you have 20. And so in the single precision, 32 bits, you have one sign bit. There's always a sign bit. You have 8 exp bits, and you have 23 frac bits. In double precision, you have 11 exp bits and 52 frac bits. Now, there's a number of different kinds of floating point representations. The sort of the default and sort of the common representation is called normalized, so-called normalized values. And normalized values are all the values where the exp field is not equal to 0 and not equal to all zeros and not equal to all ones. Okay, so everything, all zeros and all ones are special kinds of numbers we'll look at in a second. So the exponent, this exponent e, remember our numbers are -1 to the power s times m times 2 raised to the power e. The exponent e is encoded as this biased value which is called exp. So the exponent e is exp minus some bias. And exp is the value, capital exp is the value of the exp bits, the bits in the exp field, treated as a positive number. Okay, so capital exp is just, you just look at it as an unsigned 7-bit, in the case of single precision, 7-bit number. Okay, now the bias is 2 to the power k minus 1, where k is the number of exponent bits. Okay, so for single precision, we have 8 exponent bits. So 2 to the 8 minus 1 is 7. So 2 to the 7th is 128. Minus 1 is 127. Okay, so the bias for single precision is 127. And similarly for double precision, it's 1023. Okay, so you just have to memorize this formula. The exponent e is the exp field interpreted as an unsigned number minus the bias. Now this is kind of a strange thing. The first time you encounter floating point, it seems kind of odd, right? So why not? I mean, we've already learned about 2's complement. That's a perfectly fine way to represent positive and negative numbers, right? And we have exponents that are negative and positive, right? So why not just use the exp field to represent, or why not just use 2's complement in the exp field to represent those positive and negative exponents, right? So it turns out that the reason that they do this is that, and if you think about this, and we'll come back to it, but if we encode the exponent e using this bias representation, the smallest negative exponent is represented by all zeros. Okay, and the largest exponent is represented by 0, 1, 1, 1, 1. Okay. So the number with the smallest exponent, if we were just to compare the bits using just some kind of unsigned representation, just comparing the bits, treating it as an unsigned number, by using this biased representation, we can just compare 2 floating point numbers just as unsigned. We can treat the whole floating point number as an unsigned integer and compare 2 numbers and get a true comparison. Okay. So the exponent uses this sort of biasing encoding. And then the significand is encoded with an implied 1. So, and this is where the normalized, in the normalized representation comes from. That we're always going to represent our numbers. So m, we're always going to normalize m, no matter what the number we want to represent. We're always going to normalize m as 1 point something. And then we adjust the exponent accordingly. Right? So if the value we want to represent is 100.01, we're going to shift it over, and it'll be 1.00. Okay. And then we'll adjust the exponent to represent that shift. Okay, so the bits in the frac field, xxxxx, are all of the numbers to the right of the binary point. Right? So there's always this implied 1, but we don't even encode it. We just throw it away because it's always there. Right? So this is a little trick just to get one more bit for free. Okay, so the xxx bits in the frac field are all the bits to the right of the binary point after 1 point, the 1 point. And this is the smallest frac field is all zeros, which corresponds to a significand of 1.0. Okay? And a frac field of all ones corresponds to 2 minus epsilon. So that's 1.11111, and so on. So let's look at an example. So let's look at how we would encode 15213, which is our favorite number, in floating point. So if we represent that, so it's an integer, and we represent it using these bits, take my word for it, correspond to the integer 213. So now we want to convert it, we want to normalize it by expressing it as 1.110 and so on times 2 to the 13th. Okay, same number, we just normalized it so that there's always this leading 1. So the significant m is 1.11011 and so on. The frac field is everything to the right of the binary point. So we throw this 1 away, and we just take the values to the right of the binary point, and then we pad it out with zeros to get the 23 bits that we need for single precision. Okay, so now we've got our frac field. The exponent, so in this case, right, E is, we're multiplying by 2 to the 13th. So E is 13. So we want to represent the value 13 using this biased encoding. So the bias is 127. And so the exponent, the value of the EXP field should be 140. Because if we take 140 minus 127, we get 13. Okay, so 140 is represented using these 8 bits, and that becomes our EXP field. Okay, so the resulting floating point number, and of course it's a positive number, so the sign bit is 0. So the resulting floating point number has the 8 bits in the EXP field that we computed by subtracting 127 from 140, and then the frac field are these bits that we got here by just taking everything to the right of the binary point. So let's look at this exponent just a little bit more, because I think it can be a little confusing. So in our example, if we want to look at the range of EXP, so what's the smallest value of EXP? What's the smallest value of EXP? Now wait a minute, don't confuse the encoding with the value it represents. EXP is just the encoding. So what's the smallest value of EXP? 0, that's right. Okay, and the largest value is what? Remember? What's the largest value? Yes? Well, the largest value would be, remember, it can't be all 1s. Right? So the largest value would be 2 to the 8th minus 1. So, okay, so the largest value would be 0, 1, 1, 1, 1, 0 followed by 7 ones. Okay. So that's 2 to the 8th minus 1 is 255. Good. Okay, so then what's the range then of?
That doesn't sound right to me. well, let's do Kling REPL. Can I get pound include my history? Okay. Standard IO. Cool, I can do history search. That's nice. Let's do a printf, and I'm gonna do a cast on a value, literal. So this will be a uint 8t. Yep. And the literal is gonna be 0x. So this will be 7f. So f would be all 4 bits, and then 7 would be another 3 bits. So 127. Seems wrong. Well, let's do just a temporary Vin buffer here. So we have 0, 1, 1, 1, 1, 1, 1, 1. So the first bit is going to give us 1, a 2, a 4, and an 8. And then we get a 16, a 32, and a 64. Okay, all these are going to add up to, yeah, so it'd be it is 127. Huh. Why was he saying 256? Oh, maybe if you had all ones. So all ones would be 255, but then you have to subtract a 1 off there. So this would have to be a E. Yeah, I think 254 is the max, according to what he said there.
So what's the smallest value? So what's the smallest value of exp?
0.
Okay, and the largest value is what? Remember, what's the largest value? Yes. Well, the largest value would be, remember, it can't be all ones. Right? So the largest value would be 2 to the 8th minus 1. So, okay, so the largest value would be 0, 1, 1, 1, 1, 0 followed by 7 ones. Okay. So that's
he's multiple kinds of wrong here, because 0 followed by all the ones is 127. If you meant to say all ones and then a 0, that would get you to 254, but still wouldn't get you to 255, which is what he originally said, which would be all ones.
1 is 255. Good. Okay, so then what's the range then of E, which is the actual value that we want to encode? Okay, remember, use this. We have this definition. So we have the range of values for exp. We have our bias. So what is the range of values for E? This is the actual exponents that we're encoding. So what's the smallest exponent? Minus 127. Good. Right? Because that's 0 is our smallest exp minus the bias, which is 127. Okay, so the smallest value of E is 127, and the largest value of E is so if we take the largest value of exp, that's 255 minus 127, 128. Okay, so the numbers that we can represent using this bias notation will have the smallest exponent will be 2 to the minus 127, and the largest exponent will be 2 to the raised to the power 128. Okay, so do you see what's going on here? So we have a range of values for E. Here's the largest value. Here's the smallest value. Here's 0 right in the middle. These are the values we want to represent. This biasing is like a shift. Now we're shifting up by 127 so that now the smallest exponent is represented by 0. Okay. Any questions about that? Now, this normal.
So what he has on the paper seems right to me, but it doesn't line up with what he's saying in the lecture. I guess we'll see from the reading.
These normalized values always have this implied 1, okay, which when we want to represent numbers closer to 0, that limits us, right? So there's another type of floating point number called a denormalized value, which is characterized by an EXP field of all zeros. And in a denormalized number, or denorm, there's no implied 1. Okay, so the significant m is encoded identically in the frac field. So there's no implied 1, and all of the numbers are the form 0 point something 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 after them. And the exponent value E, instead of, you remember for denorms we subtracted bias from, it's characterized by a large shifting. Now, these normalized values always have this implied 1, okay, which when we want to represent numbers closer to 0, that limits us, right? So there's another type of floating point number called a denormalized value, which is characterized by an EXP field of all zeros. And in a denormalized number, or denorm, there's no implied 1. Okay, so the significant m is encoded identically in the frac field. So there's no implied 1, and all of the numbers are the form 0 point something 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 after them. And the exponent value E, instead of, you remember for denorms we subtracted bias from EXP. For denorms we subtract the bias from 1. Okay. Now if we just use the definition we use for normalized numbers, that would be the EXP would be 0. So we don't do that. Instead, E is 1 minus the bias. And then the significant is coded with an implied leading 0 instead of a leading 1, like I mentioned. So when EXP is 0, and also, I mean, think about it. If we only had denormalized numbers, we wouldn't be able to represent 0, right? Because there'd always be a 1 in there. So for denorms allow us to represent 0, and they allow us to represent values that are very close to 0. So when the exponent is 0, and the EXP field is 0, and the frac field is 0, then this is the 0 value. And so this is nice because all zeros represents 0, which is sort of what you want. Now there is this sort of weird thing though that if you have the sign bit is 1 and then your frac and EXP are 0, then you have negative 0. So you have this kind of odd situation where there's a positive and negative 0. Okay. And other values, if EXP is 0 and you have a non-zero frac, then those are the equally spaced numbers that are closest to 0. Now there's a couple of other special values. When EXP is all 1s, and the frac is all zeros, this represents the value infinity. So this is a value that, that we get when we do some kind of addition or multiplication and we overflow. So in floating point always overflows to this special value called infinity, either positive or negative infinity. So it's different from 2's complement, right, where you sort of overflowed in this modular way back around into the range of numbers. In floating point, we just overflow to this sticky value called infinity, and then everything we do on that remains infinity. So for example, if we did a if we did 1 divided by 0, or minus 1 divided by minus 0, we'd get positive infinity. If we divide 1 by 0, negative 0, we get negative infinity. The fourth kind of special case, special number, is the case where the exponent, again, is all ones, but the frac is non-zero, any non-zero value. And this represents what's called not a number. So this handles cases where there's no answer. There's no feasible answer. For example, if this represents what's called not a number. So this handles cases where there's no answer. There's no feasible answer. For example, if we try to take the square root of minus 1, what we'll get back is not a number. So I think it's helpful to visualize the number line now. So we have positive 0, negative 0, sort of right next to each other. And then to the right of that are the positive d norms. And then those sort of transition into the normalized numbers. And then you have infinity, positive infinity. You have a similar situation for the negative numbers. And then you have infinity, positive infinity. You have a similar situation for the negative numbers. And then you have infinity, positive infinity. You have a similar situation for the negative numbers, and then negative and positive not a numbers. So I think you've probably discovered now that a really good way to try to understand these numeric encodings is just to do examples with only a few number of bits. If you want to understand, like for example in 2's complement, if you want to understand Tmin and Tmax and how they relate to each other, just do a 3-bit 2's complement system. Imagine you just have a system with 2's complement, 3 bits, and then you can just enumerate all the possibilities, and you can see, and then you see where, the Tmin is actually 1 greater than Tmax. So if you add 1 to Tmax, it actually overflows into Tmin. Similar thing for floating point. It's I would really encourage you to do this. Just try some simple examples with with a small number of exp and frac bits. So in this case, we're going to look at a floating point system based on IEEE that has 4 exp bits and 3 frac bits. As always, the sign bit is the most significant bit, followed by exp, followed by frac. Okay, so this is identical to IEEE floating point except for the size of the exp and frac fields. So it's actually small enough that we can now just enumerate these values, and and now you can start to see why these weird definitions for the exponent in d norms and normalized numbers. So let's just look at. So what we've done here, we've just with a sign bit of 0, we've just enumerated all of the 2 to the 7th possible combinations of EXP and frac fields, starting with 0. Okay, so when EXP is all zeros, that's a d-norm, right, by definition. And then we have the 3 frac bits are all 0. Okay, so remember the EXP is all zeros, right? So for d-norms, the exponent value is 1 minus the bias. Our bias here is 7. Okay, so 1 minus 7 gives us a value for the exponent of minus 6. So we're going to take the frac, the bits in the frac field, times, so m is 0. So m in this case is 0 times 2 to the minus 6th gives us 0. Okay, so this is our representation of 0. And like I said, it's nice that it actually is. If we just treated this as an unsigned integer, it would be 0. Okay, so that's kind of pleasing. Now let's look at the very next number, right? The EXP is still 0, and we've just bumped up frac by 1. Okay, so again, it's 1 minus the bias, which is minus 6. And now this frac field represents, this is 1/2, 1/4, 1/8. So it represents, so this is a value of m is 1/8. So 1/8 times 2 to the minus 6, which is 1/64, equals 1 over 512. So in this floating point system, the smallest non-zero number we can represent is the denormalized representation of 1 over 512. The next smallest number is 0. Right? Okay, now let's look at, so let's bump this up by 1. So now we get a frac field of 0, 1, 0. So this represents 1/4. So em is 1/4. The significand is 1/4 times 2 to the minus 6. So 2/8 times 1/64 is 2 to the 512. Okay, so the numbers were just by incrementing this by incrementing our significand, we're increasing the numbers by 1 over 512. Now the largest d-norm in this number system is the case where the frac field is all ones. And so this encodes 1/2 plus 1/4 plus 1/8, which is 7/8. And then our value is 7/8 times 2 to the minus 6, or 1 over 64, and that equals 7 5/12. So this 7 over 5/12 is the largest denormalized number we can represent in this system. And now if we bump our number up by 1, the frac field resets to 0, and now the EXP field goes from 0 to 1. Now, because the EXP field is non-zero, this is no longer a denormalized number. It's a normalized number. Okay, so now we're changing the definition of E from 1 minus the bias to EXP minus the bias. So what's EXP in this case? 1. Minus 7, the bias, is minus 6. So lo and behold, it's the same exponent as the previous denormalized number. So this is actually very clever by the IEEE folks, because you get this nice smooth transition from denorms to norms, to normalized. So you can see that our exponent E is minus 6 still. And now because we're taking 1 minus the bias 7, and our significand, now remember this is a normalized number because the EXP field is non-zero. This a frac field of all zeros represents a significand of 1.000. Okay, so this normalized number, the smallest normalized number, is 1.000, which is 8/8, times 2 to the minus 6, which is 1 over 64, which gives us 8 over 512. So we've made this nice smooth transition from 7 over 512 to 8 over 512. And I'll do one more. I don't want to. So if we bump, keeping the EXP field at 1, if we bump our frac field from 0 to 1, now this represents the significand of 1.001, which is 8/8 plus 1/8. Okay. So that's 9/8 times, and then the value is 9/8 times 2 to the minus 6, 1 over 64, which is equal to 9 over 512. Okay? Any questions about that? Question back here?
Yeah. How do you choose the bias? Like, how do you choose the bias to start with K-1?
Okay, the question is why do you choose the bias to be 2 to the k minus 1 minus 1? Well, go back to my finger diagram here. So this is the range of EXP fields that you want to, this is the range of E that you want to represent with 0 in the middle. Okay. And so you want to bias it so that this is halfway. 0, the smallest exponent is halfway to 0. So you want the bias to shift it up so that the smallest value of EXP corresponds to the smallest exponent. Right? So 2 to the k minus 1 minus 1 is just giving you a value that's halfway between the smallest exponent and the largest exponent. Okay. That's good. Any other questions? Okay, if we take a smaller 6-bit format, same thing as we did before, just different numbers of bits in EXP and frac, and then we plot these on the number line, you can see that the values are very dense around 0, so they're spaced very closely together. And then every time you increase the exponent by 1, the numbers are spaced twice as far apart as the numbers that were represented by the previous exponent. So you can see, like in this little example, you see these values here are all equally spaced. These 4 values are equally spaced, and they're right next to each other. And then you see this jump in the spacing. That represents an increase in the EXP field by 1. And then that spacing doubles as we go out. And you can see it even better here. If we zoom in, these blue values are d-norms, and then we have the next set of normalized values where the frac field is 1. They're spaced the same, right? We saw this when we kept increasing by 1 over 512. And then we increase the exponent by 1, and the spacing doubles. Increase by 1 over 512. And then we increase the exponent by 1, and the spacing doubles. Okay, so this, like I mentioned, this encoding has some pretty nice properties. The floating point 0 is encoded as integer 0, which is nice. And with the exception of not a number, you can compare any floating point numbers, including infinity, by just treating it as doing. with the exception of not a number, you can compare any floating point numbers, including infinity, by just treating it as doing an unsigned comparison. So that's really nice too. Now, when you add and multiply floating point numbers, right, we're dealing with a limited set of bits here. So if we take two numbers encoded as floating point and we add them together, there's no guarantee that we'll be able to fit all those bits in the bits we have available to us. There's no guarantee that we'll be able to fit the bits in the result. So what we do in this case is, you can imagine the model you want to have of floating point operations, addition and multiplication, is that you add or multiply, you do the addition or multiplication, and you compute the exact result. You just assume that you have an infinite number of bits. And then you use a technique called rounding to get it to fit into the available bits. Okay, so the effect is, like of doing, say, x plus y is getting the precise value of x plus y at an infinite number of bits and then rounding into the available bits. So let's look at this idea of rounding. This can be confusing the first time you see it. It requires, you need to think about it carefully to get it right. Now in IEEE there's 4 different kinds of rounding. There's round towards 0, round down, round to minus infinity, round up to, which is rounding it to positive infinity, and then the default case, which is the only one we're really going to consider, which is round to the nearest even. And this is what IEEE does by default. You can, if you go into assembly language, you can change the rounding, but we're not going to consider it anymore. Yes, question?
Is there a distinct negative infinity apart from the positive infinity?
I'm sorry?
Is there a distinct negative infinity apart from positive?
There is, right? Because there's one. So the question is there a distinct negative infinity and a distinct positive infinity? And there is. They have the exact same bit representation, except the most significant bit for negative infinity is 1. And for positive infinity, it's 0. Okay. Yes, question?
Why does nearest even round to 1 for 140?
Why does nearest even?
Round to 1 for 140.
Oh, I'll show you. Let me go over the others. The question was about nearest even. Yes?
Doesn't that make negative infinity greater than positive?
Well, that was the exception, right? That's right. So aside from infinity, you can't do that comparison.
But how about
Positive infinity works, right? But not negative. So you're right. Good point. All right. So let's look at these rounding modes, and I'll explain why the nearest even works. But let's look at, so rounding towards 0, what we're going to do, we'll use dollars. So we want to round to the nearest dollar. Towards 0, just anything less than, you just round towards 0. So $1.40 would go to 1, $1.60 would go down to 1, $1.50 to 1, $2.50 would go to 2, negative 150, you round towards 0, so that would be negative 1. Round down towards negative infinity, it's similar. The only difference is that for negative $1.50, you'd round towards negative infinity, which would be minus 2. Rounding up is symmetric to round down. The interesting case is round to nearest even. Interesting because it's what IEEE floating point actually uses. So the idea here, if you have a value that's less than half, then you round down. If you have a value that's more than halfway between two dollar amounts, you round up. The nearest even part comes when you have something that's exactly halfway. Then what you do is you round towards the nearest even number. Okay. So in this example, $1.40, because it's less than half, rounds down to $1. $1.60 is greater than half, so we round up to $2. $1.50, right in the middle, we round up to the nearest even dollar amount, which is $2. $2.50, we round down to the nearest even, right? If we round it up, it would be 3, which is an odd number. And minus $1.50, we round to we round down to minus $2. So the reason we do this, the reason they chose this, is that statistically, if you would imagine, if you have a uniform distribution of sort of numbers, they're going to round up or down about 50% of the time. So there won't be a statistical bias rounding up or down one way or the other. Okay, so that's the reason they did that. Now, you can apply the to any value. So in the last example, we did it to the nearest dollar. But suppose we wanted to round to the nearest hundredth using round to even, the default round to even mode. We want to round to the nearest hundredth is this second position. This first we have tenths, then hundreds. So if we have a value 7.894999, that's less than halfway, right? Halfway would be any number that had a 5 followed by all zeros. So 4999 is less than that. So we would just round down to 7.89, even though 9 is odd. The only time we're going to apply round to even is when we're exactly halfway. Okay, the next example, 7.895001, that's greater than halfway, right? If this was a 0, it would be exactly halfway. So we round up to 7.9. Okay, now here's the interesting case where we have 7.895 followed by all zeros. That's exactly halfway. So now we apply the round to nearest even rule. 9 is an odd number, so that doesn't work. So we round up. And we do that basically by adding a 5 here. So 5 and 5 is 10, and then that carries over to the next position, and 9 and 1 is 0. 9 and 1 is 10, so that carries over, and so 8 plus 1 is 9. So the result is of rounding up is 7.90. Okay, is that clear? Do you see? It's a very mechanical way. When you round up, it's a very mechanical like that. You always just add the halfway number, in this case 5, and then just propagate it out. Just do the addition, and that'll give you the nearest. That'll round you up to the nearest hundredth in this case. Okay, now the last case, 7.885 followed by all zeros. That's another number that's halfway between two numbers rounded to the nearest hundredth. So in this case, 8 is even, so we round down, and to round down we just truncate. Just throw these bits, these digits away, and we get 7.88. So are there any questions about this? Question back here, yes?
I have a question kind of going back to the slide, not exactly this. But so is it true that everything of the same exponent or that has the same x field will be equivalently spaced? Is that how it works?
Yes, so the question was if numbers that have the same exp field, will those numbers be equally spaced on the number line? And the answer is yes. Yes, question?
Yes, so I want to ask if when we're rounding up or down, we consider all the, the entire value to the right of the place we're rounding. Like if in the last example, there was a 1 at the end, it would round up.
It would round up. Yeah, the only, the halfway values are always, in this case, because it's base 10, the halfway number in base 10 is 5. And then so it's always the halfway number, in this case 5, followed by all zeros. You'll always have the halfway, if a value is halfway between like 2 hundredths, it'll always have that form. All right. Now we can do the same thing with binary fractional numbers as well. Now a binary number is even if the least significant digit is 0. Okay, we only have 2 digits, right? So odd is 1 and 0 is even. Okay, and the halfway, so the halfway value is going to be a 1 followed by all zeros. Okay, that represents exactly halfway. Okay, so it's analogous to the base 10 example, except where the halfway value is going to be 1 followed by all zeros. So let's look at some examples. So suppose we want to represent 2 and 3 30-seconds. And suppose we only have 4 bits to do that in. Okay, well, to represent that exactly, we need 7 bits. And so we have to round. Okay. So let's look at, so we're going to round to this 2 bits right of the binary point. And so let's look at all the bits that follow that. So since it starts with 0, this is going to be less than halfway. So since it's less than halfway, we just truncate, just chop those out, and the result is 10.00. Now our next example is 10.00110. So if we look at these, the bits to the right of the bit we're rounding to, since it starts with 1 and it's not followed by all zeros, that's greater than half. Okay. So in this case, we have to round up. And so the way we do that is we take 1 and we add it to this leftmost 1 right here and just do the addition, and the result is 10.01. Now let's look at 2 to the 7/8. This is represented as 10.11100. Now here's that halfway marker that we were looking for. It's a 1 followed by all zeros. So this is exactly halfway. So now we have to round to the nearest even number. Now, if we can't just truncate, because then that would be an odd number, right? It would end 0.11 is an odd number. So we have to round up, and we do that by adding a 1 right here to this leftmost red bit. We add 1 to that, and then just do the addition, and we end up with 11.00, which is 3. So the nearest value to 2 to the 7/8 the nearest rounded value is 3. Okay, our last example, 2 to the 5/8, we have the same halfway marker again, 1, 0, 0. But in this case, the hundredths bit, or the 1/4 bit, is 0, so that's even. So we can just truncate. We just throw those bits away, and the result is simply 10.10. That make sense? So it's very mechanical. Mainly, you just need to be able to recognize that halfway marker and then figure out if you need to round up or down. If you're going to round down, just truncate. If you're going to round up, add a 1 and just propagate it to get your result. Okay. Now, we won't spend much time. I just want to mention a few things about multiplication and addition. So if we multiply two numbers, so we have different mantisses, significance, and exponents, and suppose that the result is m times 2 to the e, the sign bit will be the XOR of the two sign bits of the two operands. The significant m will be the multiplying m1 times m2, and the exponents are added, right? Because just by the rules of exponents. So if m is greater than 2, and this is a normalized number, we have to shift it. We have to put it in the range between 1 and 2 by shifting to the right and incrementing the exponent. If e is out of range, then we overflow to infinity. And then if m has too many bits, we have to use round to even to fit it into the available frac bits. Okay, addition. So suppose we're trying to add two floating point numbers. Conceptually, what you do is think of those numbers as fractional binary numbers. You want to line up the binary points. Then do the addition, and then do the addition, and then normalize the number so that normalize the significance so that it's between 1 and 2. And apply two. Now we won't add a 1. I just want to mention a few things about multiplication and addition. So if we multiply two numbers, so we have different mantisses, significance, and exponents, and suppose that the result is m times 2 to the e, the sign bit will be the XOR of the two sign bits of the two operands. The significant m will be the multiplying m1 times m2, and the exponents are added, right? Because just by the rules of exponents. So if m is greater than 2, and this is a normalized number, we have to shift it. We have to put it in the range between 1 and 2 by shifting to the right and incrementing the exponent. If e is out of range, then we overflow to infinity. And then if m has too many bits, we have to use round to even to fit it into the available frac bits. Okay, addition. So suppose we're trying to add two floating point numbers. Conceptually, what you do is think of those numbers as fractional binary numbers. You want to line up the binary points. Then do the addition, and then do the addition, and then normalize the number so that normalize the significance so that it's between 1 and 2. And you either do that by shifting right or left. If e is too big, then you overflow, and then you round the bits in m to fit into the available frac field. Now, you remember when the first day of class, we talked about what we call these great realities, that ints aren't really integers and floats aren't really reals. So the and just as we saw when we looked at 2's complement representation of integers, it's not exactly, they're not exactly like real integers, and operations on them aren't exactly like real integers, but they follow very predictable mathematical properties, okay, that are similar to integers, but not quite. So the same thing holds for floating point numbers. They follow very predictable, they have very predictable mathematical properties, but they're somewhat different from the reals. And the big thing is that the big thing with addition is that it doesn't associate. Okay, it's commutative, but it's not associative. And this usually happens when you're dealing with numbers that have very large dynamic ranges. So if you're trying to add and subtract really big numbers with really little numbers, you run into this problem of non-associativity. So the example was if we take 3.14 plus 2 to the 10th, 2 to the 10th is so much larger than 3.14 that when the bits that, it would be 2 to the 10th plus 3 to the 0.14, the bits that represent the 3.14, there's bits way out here that represent, there's one bit out here that represents 2 to the 10th, and then there's a few bits here that represent 3.14, and there's just not enough, we don't have enough bits to represent all those, so we have, the 3.14 goes away. So adding a big number to a little number essentially gives the big number, and then if you subtract that big number, you get 0. Now, if we change the association, if we take this big number and subtract it from itself, we get 0, and then so the result will be, instead of 0 as before, we get 3.14. So other than that, you have all of the things that you would normally expect. Closed under addition, it's commutative, there's an additive identity of 0. Except for infinities and nans, there's an additive inverse. Right? You can take, for any number, there's an inverse that'll give you 0 when you add it together. And you get monotonicity between values, except, of course, for infinities and nans. Now, multiplication has, it's similar. It's closed generally under multiplication. It's commutative, but it's not associative, and it doesn't distribute over addition. And it's the same. So here you can see we're taking 2 to the 20th times 2 to the 20th times 2 to the 20th, and so that gives infinity. But if we reassociate and we take, 2 to the 20 times 2 to the 20th times 2 to the minus 20th. Well, this first multiplication is infinity, and anything you do with infinity is just infinity. So the result is infinity. However, if we reassociate and multiply 2 to the 20th times 2 to the minus 20th, that gives us 1, and then multiplied by 2 to the 20th, and so we get 2 to the 20th. So the big takeaway point here is that a floating point isn't associative. Okay. Now, is that a problem? It's something you have to be aware of, but generally, I mean, I've done a lot of scientific computing, in particular modeling earthquake ground motion in Southern California. So basically, we would build models of Southern California in the computer, and then we would shake them, and then we would see how the ground moves in, like, Los Angeles. Right? And that shaking, we used a numerical method called finite elements, and it used all floating point, single precision floating point numbers. And we never ran into a problem with this associativity, right? We would do operations in different orders. We couldn't always guarantee that we would do the operations in the exact same order. But we never ran into a problem with this because nature in general is kind of smooth, right? That if you look at if one part of the ground is shaking like this and you look at the next part, it might be shaking a little more or a little less, but you're not going to have like huge differences. And so we never ran into those kind of problems. But in some, so generally if you're simulating natural phenomena, you don't often see these kind of huge dynamic ranges. But other times, if it's not non-natural, maybe financial systems that use floating point, then you might see these larger dynamic ranges of numbers, and it might become a problem. So as a programmer, you just generally have to be aware of this. You have to have a sense for the dynamic range of your numbers, and you have to keep in mind that if you reassociate or change the order of things, you may not get exactly the same answer. Okay, now C gives us two different kinds of floating points. So the float is the IEEE single precision, and double is the IEEE double precision. Now, you remember when we did casting between ints and unsigned values back and forth, the cast never changed the bit representation. It just changed the way that, and in fact, it never even changed how the ALU manipulated those bits. It's really just how we're interpreting and how we're viewing those values. However, when you do cast between floats and ints and doubles, the bit representation changes, right? So a cast here has a dramatic effect on the actual bits themselves. Now, if we go from a double or a float to an int, it's going to truncate the fractional part and give us the integer part, and then round to fit. Oh, actually, no, there won't be. Okay, so think about this. How many there were? We said 23 frac bits in float, and I forget exactly how many in doubles. Anybody remember? Doesn't matter. It's some number. Well, no, it does matter. So for a float, if we cast a float to an int, we're casting 23, something that we can represent with 23, at most 23 frac bits into a 32-bit int. So we'll never lose. So we'll never need to do any rounding. But double precision has 52 bits. Okay, so there we might not be able to fit the represented integer into the int, so there'll have to be some rounding. Sorry, PowerPoint crashed. Right now, if we cast from an int to a double, we'll have enough bits so we won't lose anything, right? The 32 bits will fit in the double precision frac field. But int to float there's more bits in an int than there are in the frac field of a float, so we'll have to do some rounding, right? So casting works the same way as any other operation. You can think of it as just taking assume you have an infinite number of bits, get the exact result, and then round it to fit into the available bits. All right, so let's, the final thing I want to do today is sort of test your understanding, solve some puzzles to test our understanding of these properties of floating point numbers. So imagine that we have three values: x is an int, f is a float, and d is a double. And then we're evaluating these C expressions. So x, is x equal to int float x? Yeah.
Okay. For each of the following C expressions, either argue that it's true for all argument values, explain why it's not true. X is an integer, f is a float. I don't know why they didn't do I here. And d is for double. Assume neither d or f is nan. Okay. Okay. X is equal to int float x. So first, x as an integer gets converted into a float. It could then lose precision since it's a 32-bit value. Float is a 32-bit value. And the float could have not enough bits to represent the integer precisely at the higher range. So it loses some precision when it goes to a float, and then converting back to an int. So this is false. You could have a very large x that will get rounded, and precision will be lost on it when it gets converted through a float. Now a double has 64 bits, so that is true. There's more than enough space for that. A float itself going to double again has enough space for that. Going back down has enough space for that, so that's true. So it's going to be false, true, true on these first ones. Let's let him catch up.
Oh, you can edit out that other stuff?
Yeah. Okay. He did not edit out the other stuff. All right, let's let him catch up.
All right, so what do you think? If we take x, which is an int, cast it to a float, and then cast that back to an int, will that always be equal to x? No. Right, because we lose some bits, right? We don't have enough frac bits in float. What about if we take x, cast it to a double, and then cast it back to int? Will we always get equivalent value? Yeah, because we have enough frac bits in double. Now what if we take a float f, cast it to a double, and then cast it back to a float? Will that always equal the original f? Yeah.
Okay,
what about the
so taking a double, going to a float, and then go back to double, definitely you're going to lose precision on that one.
converse, though? What if we take the double d, cast it to a float, and cast it back to a double? No.
A float taking its negative and taking the negative that, so double negativing it. Yeah, I think that's fine because you're just switching the sign bit.
How about this? How about if we take f, negate it, and then negate that again? Will that always equal f? Yeah, because we're just toggling a bit, right?
Yep. And then you get 2 divided by 3 is equal to 2 divided by 3, no, because integer division versus floating point division, I'm guessing, because one of the operands on the right-hand side is float.
Okay, how about 2 over 3 equal 2 over 3.0? No, because 2 over 3 is 0. Okay. And 2 over 3.0 is a floating point value, 2/3. The floating point representation of 2/3.
All right, next one is assuming that d is less than 0, it's a double, 64 bits, it's less than 0.0. What's the implication here? Therefore, double times 2 is less than 0. Yeah, I'd say it's true.
If the double d is less than 0, does that imply that d times 2 is also less than 0? Yeah. Even if, no matter what, even if 2 times d overflows, it'll overflow to negative infinity, which is less than.
Yeah. This sign will be preserved. Double greater than f. Okay. So you have a double. The float's going to get converted to a double in the comparison. And then you compare the two and you say, okay, d is just greater than f. Then the unary negation of it, yeah, I mean, they're just toggling the sign bit on those. So d was greater than f. So negative d is going to be, yeah, that's going to be true.
It's less than 0. Okay, how about, does the double d greater than f imply that minus f is greater than minus d? Yeah, that's that monotonicity, right? And again, it's just, yes?
You said that 2 over 3.0 was a float. Is that a float or a double? Would that be a float or a double?
Oh, that's a good question. I think it'd be a float. I think if you put, there's an annotation in C to give it a double, but actually I'd have to check that out. That's
There's also one for floats, for F.
an F, yeah. That's a good question. I don't know. We'd have to check. I'll have to go and look in the.
I can check real fast. If I go over here. Oops. Should kill that. Sneeze. So I can just open up any of the test files I have here. Vim, tests, whatever. Sure. Implicit, great. Can you just give me a C file? Can you just give me a C file, please? Okay, and here we're going to say auto x is, or z is equal to 2 divided by 3.0. So it's a double. Kid was right. Kid was right. I guess the other thing I'd like to look up here is if we say auto z is equal to what was it, 3.0? Yeah, it goes to double by default. I like the other instructor. I think this guy is the lesser of the two.
How about if is d squared, the double d squared, always greater than or equal to 0?
Oh. No. Because it could be a negative infinity. And negative infinity times negative infinity, I'm pretty sure it's negative infinity. I don't think they would go to positive, would they? Maybe they would. Let's if we go here, oops. No, that's not what I wanted. And then Control B. There we go. Python. I think they have infinity. Maybe node. Infinity, yeah. So at least in JavaScript, negative infinity times negative infinity. Oh, it does figure out that's positive. Okay. So in that case, the infinity case is handled. D times D. If D is 0, that holds. If D is negative, that holds. If D is negative infinity, it holds. If D is any positive value, it holds. It overflows into a positive infinity. So that's true.
Yes.
Oh, what's the last one?
How about
here?
it?
D, F. D plus F minus D. So the double plus the float gets converted into a double, up converted, and then added to it. And then we subtract out the D is equal to F. I'm gonna say yes, because then the float would get converted up to. Is this the associativity thing though? What if D is infinity? You could say infinity plus whatever the value is minus the value. It's still infinity. Yeah, I guess the infinity case would invalidate this. Also, if the float is small and the double is big, it could get rounded off. Yes, that's false.
Squared, the double d squared, always greater than or equal to 0? Yes. And how about, does d plus f minus d always equal f? No, because of lack of associativity. Okay, so that was fun, right? Floating point's always fun. So anyway, the big thing is just to realize that floats aren't exactly really reals, but they have very, very predictable properties, and that they're not associative or commutative. They're not associative, and so you have to be careful about that. All right, well, have a good weekend, and we'll see you on Tuesday.
One can reason about operations independent of implementation, as if computed with perfect precision and then rounded, not the same as real arithmetic. Violates associativity, distributivity. Makes life difficult for compilers and serious numerical application programmers. Okay, cool. Oh, and then we got a recitation. Data lab. I want to check this out. Let's go back over here. Wait a minute. Is that we're here? Yeah, we're here. Recitation 3. They start on recitation 3. Let's just take a little peek at this.
Okay, everyone, so welcome to your first recitation. My name is Ben. I will be your TA for the semester. Just so that you know, the cameras in the back are so that we can record this recitation for the 513 students. So the topic of today's recitation is data representations. So you've been talking in class. Well, actually, first let's talk about what recitation is. So recitation is a place where we can have a little bit more of an interactive learning session than lecture. So in recitation, if you ever have a question, raise your hand so that you can ask. That's part of the point of recitation. If you want to go over an example, a particular example of something that you talked about in class that you're confused about, ask about that, and we can go over that here. We'll cover a recap of stuff from class. We'll go over example problems that'll help you for your homework, for your exams. And we'll go over demos and tips and questions about the labs as they come out. So a little bit of course news. Hopefully you've seen most of this already. So we have a course website, cs.cmu.edu/213. That's where all of the important stuff for the course is, all of the schedules, all of the labs, everything can be linked to from there. You should have access to AutoLab by now. That's how you'll actually be turning in the labs. If you don't have access to AutoLab, you should email the staff list. That address is on the website. We have office hours. There's actually a typo in the slides there in Wien Hall 5207, not GHC. But the office hours will be every Sunday through Thursday, 6 to 9 p.m. And then we will also have additional office hours near the due dates. Both some of those times will be extended, and sometimes we'll have office hours on Fridays. And you should see the website for the exact schedule of when those extended office hours are. Also, this Saturday, we are having a Linux boot camp, 2 to 4 p.m. in GASE 4401. So the Linux boot camp is if you are feeling weak on your skills with like SSH or navigating a Unix file system. If you want to learn more about how to use a text editor like Vim or Emacs that you can use over SSH, we'll be covering all of that at the Linux bootcamp because you do need to do your homeworks on either the Unix machines or the Shark machines. So this stuff will be important for you to be able to complete it. And also, Data Lab is due this Thursday, September 17th at 11:59 p.m. Hopefully, you've all at least started on it. So today we're going to talk about a couple different things. The first thing we're going to talk about is Data Lab and how you should go about doing that. And then we'll talk about integers. We'll review some of the stuff you learned in class, and we'll review some of the floating point stuff you've learned in class. OK, so Data Lab. How do you do Data Lab? First thing, you need to download the files from Autolab. So all of the lab files will be on Autolab throughout the semester. There'll be a tar with the C files and other executables and stuff in it, and then there'll also be a link to a PDF write-up on Autolab. And so you should read both of those. They both have information about every lab. Make sure that you're doing your labs on either the Andrew Unix machines or the Shark machines. For some of the labs, you'll have to use the Shark machines. The next lab, Bomb Lab, will only work if you're using the Shark machines. The Shark machines are special machines just for you guys, the 213 students and the 513 students. The login password and username is the same as your Android ID and password that you would use for the other machines. Make sure you don't untar the handout onto like your local Windows machine or something, because then it won't maintain the permission bits, and you'll get all kinds of error messages when you try to run the programs. If you do happen to get those sort of error messages, in order to make a file executable, the command is chmod +x, the file name, and then you'll be able to execute the file again. OK, so what you want to do for BitLab. So BitLab, what you have is you have a bunch of puzzles, and you have to solve this puzzle using a certain set of operations that are legal and not using more than a certain number of those operations. So there's 3 important programs that we have for you that will help you do this. So let's actually go on to the Shark machines and sort of try these out. So the Shark machine, you put SSH. Is that big enough for everyone to see it? So SSH, your Andrew ID, and then, oops, it's not going to work. It's shark.ics.cs.cmu.edu. And then the password will be the same as your Andrew password. OK, so you can see there's all these different Shark machines. If you don't put which one in particular you want to be on, it'll just pick one for you at random and sort of distribute the students across them. They reboot early in the morning, so if you happen to be working on your work that early in the morning, just be aware that it might shut down in the middle depending on which one you are. So what we have here is, so I've downloaded the Data Lab handout.tar from Autolab. And what you want to do is you want to untar it. And then what you get is it dumps it all into a directory named Data Lab handout. So if you missed the command, that was tar xvf Data Lab handout.tar. That's in the handout. And so what you see is, so you go in here, and you get a bunch of files. And some of these won't actually be in here by default because I've already started it. But what you get is you get these files in here. So the most important file here is bits.c. This is the file you'll actually be editing. So we can open it up. Oop, that's not it. OK, so what we have is we have here a bunch of instructions. Is it this small? So we've got a bunch of instructions on how to do Data Lab at the top of the file. Make sure you read those. And then what you're going to do is you have all of these puzzles. So for each one, you have a certain set of legal operations. So here the first puzzle is bit XOR. So bit XOR, you're allowed to use the negation, operator bitwise negation, and bitwise and that's it. And you can use up to 14 of them in order to do the same behavior that XOR would do. So what you want to do is you want to go in here and you want to actually implement that. So say I decide I'm going to implement it by just doing X, XOR Y, because like that's totally going to work, right? So I mean, that does the same thing as XOR. We know it does. OK, so I've done that. And now what? So now I can make. So make will compile your code, what you currently have. And what it'll do is it'll also now give you an executable called btest. So now I have the btest executable, and also gave me these other 2 programs called fshow and ishow. So now I can run btest. So btest is the first thing we have. So we have 3 ways to test our solutions: btest, DLC, and the BDD checker. Btest is the first way to test your solutions. So what does it do? It says, OK, I got a score of 1 on bit XOR and failed all of the other ones. But what we know is that I actually didn't do bit XOR right, because I used an illegal op. So btest is just checking that the answer is correct, but it's not actually checking that I followed all of the invariants in the file. So we have a second program, which is the DLC checker. So the DLC is a special compiler that will check if I followed the invariants correctly. Oops. So I run it on bits.c, and what does it tell me? It tells me, oh, I used an illegal operator XOR, because that's not allowed in that puzzle. So if you're ever not sure if what you're doing is legal or not, if you've If you want to make sure that you've used the correct number of ops, that you've only used the ops that are allowed, the DLC checker is the program that does that. And then also, we have driver.pl. So driver.pl will do two things. It'll run the DLC checker, and then it runs the BDD checker. So the BDD checker is the actual grading program that's going to be used by Autolab. Autolab uses driver.pl, the exact same script that you have here. So if I ran that, what it would tell me that I used an illegal operator in the first problem, and I got all of the rest of them wrong because I didn't do them. So right now I have a 0 out of 63. So there's a couple other things that these programs can do. So btest can do more than just run on the whole thing. You can also do a btest, and if we do -- help, we can see the different options for it. So we see that we can do btest, and we can give it, we can give it a function name. If I give it bit XOR, oops, I didn't do it right. -f. So if we do btest and give it -f, and I don't know why my terminal is doing these weird things, and bit XOR, then it will run just on that function. So if we're just working on one function, we don't want to see all of the output for the rest of them, we can use -f. Now say we're working on it and we want to actually try it out on some particular values to see if it works on those, then we can do btest, we can give it a function, and we can do -1 and give it one argument, and -2 and give it another argument, and it will run it on those things and tell you if it passed on those or not. So my implementation does work for 9 and 34, which is unsurprising because it does just use XOR. So we could do the same thing if we reopen bits.c. Say now that I've realized from the DLC checker that this is not a legal way to do it, and so I'm going to try it just by doing this instead. I'll just bitwise and them, because that's a legal op and it's less than 14 of them. So I do that, and then what we want to do is we need to remake so that we'll get recompile the program. Okay, and so now we can do btest on bit XOR, and it failed, and it gives me a counterexample of where it failed. So if we give it intmin and intmin, bit and is not the same as bit XOR. But if we run the DLC compiler on it, we can see that at least I followed all of the invariants. So those are the different programs you want to be using. In addition, there's also two more. You can see two more programs in here, fshow and ishow. So fshow and ishow are utility programs to help you. So fshow, we can look at the help for it. Oops, that's not how you get the help for it. Well, it tells us the usage anyway. So you give it some values as either hex or floating point numbers, and it will tell you stuff about the bit patterns that those have. So if I give it 0, it tells me that the bit representation of 0 is just all zeros, but the sign, exponent, and fraction bits are all zeros, and that is a denormalized number. So this is useful for you once you get to the float puzzles if you want to know things about particular floats. We can do the same thing and say give it 1.5, and it'll tell us the floating point representation of 1.5. And then we also have ishow. So if we want to see some decimal numbers, we can see that 42 is hex 2a and is an unsigned and signed integer with value 42. Okay, so any questions about the data lab programs and how you go about solving that and knowing if you're correct and checking your solutions as you go? No questions? Okay, good. So that's it for that. Okay, and then the last thing you do once you've actually finished data lab, or if you're partway through and you want to checkpoint your progress, you can submit to Autolab. You have to submit through the website. We don't have a check-in script like you might have had in 122 or anything. You just have to submit through the website. In order to get a tar file out of your files that you can submit to the website, that's the command you want to use there. It should be in the handout too. Okay, so a couple other things about BitLab. So the DLC checker will check that you have used the correct number of ops, that you've only used legal ops. But it also has a couple different constraints. It's a modified compiler from MIT or somewhere that's like really old. And that means that it has some style guidelines that you have to follow that you wouldn't normally need for modern C code. So all of your variable declarations need to be together at the top of a function. So even if you don't use it yet, you need to put all of the variables declared before you do anything else. You need to make sure that the closing brace for the function is in the first column and that none of the other closing braces are in the first column. We won't be using this compiler for the later labs, so you just have to worry about this for now. In the future, you'll be able to write C as you normally would. Also, you should think about operator precedence and like use parentheses to be very explicit about it. Does anyone know what the precedence is of those things are relative to each other? I mean, why would you? Do you really even need to have? What it is the unary negation binds the tightest, and then times, and then plus, and then the bitwise shift. But maybe I'm wrong, and so use parentheses. They're free. You don't have a limit on the parentheses. It'll help you out so that you're not making mistakes by writing something down that is different than what you thought you wrote. You should take advantage of special operators if you're allowed to use negation. Use negation. 0 is a useful number. Int min is a useful number. You should try to work these into your puzzles. They'll help you out. And once you've gotten down to the required number of ops, using only the legal ones, you have full credit. If you want to reduce it more just to get higher on the scoreboard, you can, but you won't get any more points. Also, you should worry about undefined behavior. So shifting by greater than 31, bit shifting by greater than 31 bits or by a negative number of bits is undefined. Here's a little bit of an excerpt from the x86 reference about what shifting by more than 31 does. So it just takes those extra bits and it puts them into a flag.
Let's read this from the Intel x86 reference. These instructions shift the bits in the first operand to the left or right by the number of bits specified in the second operand. Bits shifted beyond the destination operand boundary are first shifted into the CF flag, then discarded. At the end of the shift operation, CF flag contains the last bits shifted out of the destination operand. The destination operand can be a register or a memory location. The count operand can be immediate value or the register CL. The count is masked to 5 bits, which limits the count range to 0 to 31. A special opcode encoding is provided for the count of 1. The masking part
thrown
is
away, it
important.
just ends up in the flag in the end. And then your program will execute differently if that flag is used somewhere later along the line. So you should worry about that and make sure you don't do stuff that's undefined. And there's some assumptions that you can make. In bits.c, it tells you about some assumptions you can make about the behavior. OK, so any other questions about data lab? OK, so now we're going to do a little bit of a review from class. So you've been talking about data representation. And 2 of the things you've talked about are integers and floating points, right? We've talked about how we represent integers and floating points on modern computers. So integers are simpler than floating points. We have signed and unsigned integers. If we have an unsigned integer, then it represents the number 0 through 2 to the however many bits we have minus 1. And if we have an unsigned integer or a signed integer, then we can do from negative 2 to the number of bits we have minus 1 to 1 less than that in the positive, because 0 is a non-negative number. So a couple of the interesting things we can do with integers is use bit shifts to simulate multiplying and dividing. So multiplying and dividing are pretty slow on the actual machine relative to the other arithmetic operations. But bit shifting is really fast because you're just moving things left and right. So if we want to multiply a number by a power of 2, we can just left shift by that many bits. So why does this work? So if we have a number in binary, what does it represent? So we've got some number. And what are these? This is the bit that's 2 to the 0. This is the bit that's 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and so on. And so a binary number is just like a sum of powers of 2. And so when we left shift, which pads with zeros, say we left shift by 1, then what we get is we'll have a 0 here, and then all of this gets pushed over. And what does that do? That means that this 2 to the 0 became a 2 to the 1, so it got multiplied by 2. This 2 to the 3 became a 2 to the 4, it got multiplied by 2. All of the 1s get multiplied by 2, so the new sum is twice as big, because this number is a sum of powers of 2. So does that make sense, how left shifting is the same as multiplying by a power of 2? Yes? OK. And then we can also do the same where we right shift to divide by a power of 2. But now it gets a little bit more tricky. So for positive numbers, the story is the same. We just right shift, and then it's the same as bumping them all down by whatever amount we want, and then we've divided by that power of 2. But what about negative numbers? What's the problem with negative numbers? This is on the slide, so if you don't remember, you can read it and then tell me. What's the problem with negative numbers? It's going to round towards negative infinity, but we want the division to round towards 0, right? So say we have a negative number. So how about let's work with, let's see, I had an example. So let's try out, let's say we have a 4-bit 2's complement system. So what does that mean? That means we're going to have 1 signed bit and then 3 other bits, and that's how we're going to represent our numbers. So say we have the number, say we have the number 1010. And this is 4 bits, 4 bits, 2's complement. What's the decimal number that this is equal to? From base 2, what's this in base 10? Does anyone know? 10? So this, yeah, so this is 2's complement, so this is a sign bit, so this is a negative number. I heard someone say it. Negative 6, right. So how did we get negative 6? So I'm using this little subscript notation to note if I'm writing the number in binary or decimal. So 2 for binary, 10 for decimal. So yeah, how did we get negative 6? So the sign bit is 1. So when the sign bit is 1, that's a negative 8 because we have 4 bits here. And then this is a positive 2 that we've added back into that, so that leaves us with negative 6. And so like if we had a 1 here, that would be adding 1 more, and it would be negative 5. OK, so we have negative 6. Say we want to divide negative 6 by 4. So we want to divide this by 4, and we're going to try doing that by just shifting to the right by 2, because 4 is 2 to the 2. So what do we get? So when we do an arithmetic shift, so there's 2 types of shifts that we can do, logical and arithmetic. And when we do a logical right shift, what that means is you just pad with zeros, the extra things that are showing up on the end. And that can be used to divide unsigned numbers. But since we're working with a signed number here, we want to do an arithmetic shift, which pads with the value of the sign bit. So when we have a negative number, it pads with 1s, and we have a positive number, it pads with 0s. So we do a right shift, arithmetic right shift by 2. And so what do we get? So we get 2 1s for the padding, and we have this 1 and 0 here. This is binary. So what number did we end up with? Negative 2, right. So we ended up with negative 2. But what is negative 6 over 4 rounded towards 0? So rounded towards 0, we want a negative 1, because this is equal to negative 3 halves. We're rounding towards 0, so since it's right between negative 1 and negative 2, we round towards 0 as negative 1. This didn't give us the right thing. This truncated those extra bits. It just threw them away and rounded towards negative infinity. So we need to do something a little bit more interesting, a little bit more complicated in order to divide a signed number that's negative just by using bit shifting. So the solution is something called biasing. So what we do, so biasing. So we want to add 2 to the k minus 1 to our number before we shift, where k is the number of bits we're shifting. So what does that do? So in this case, so we have this number. We're shifting by 2 bits. So we're going to add 0, 0, 1, 1 to it. And so what this is going to do is if there's any bits here in this bit that would have been truncated before, what's going to happen is adding this will cause it to show up over here. And so then instead of these bits being completely ignored and just thrown away by truncation, it will allow it to round. So when we do this, what we see is that we get 1, 0, and then we carry 1, 1. So we add the bias, and now we shift by 2, padding with 1s because it's an arithmetic shift. And we get 1, 1, 1, 1. These 2 got thrown away. These 2 got shifted over, and there's the padding. And so what's this equal to? This is equal to negative 1, which is what we wanted. So does it make sense how adding this bias allows us to round towards 0 rather than rounding down towards infinity by preventing us from just throwing away these extra bits if they're non-zero? And if these are 0, well, then adding doesn't really do anything because there isn't going to be any carry bit into the part that doesn't get cut off by the shift. Does that make sense to everyone so far? Yes? OK. So that's a little bit of integer division. So a couple other notes about integers. So one of the properties of integers that we care about is endianness. So endianness says, well, which bit is most significant in a binary number? What order are these bits stored in memory? And you don't really need to worry about this quite yet, but very soon, once BombLab is out, it will matter because you'll want to actually make sure you're reading off the bits correctly. So what does endianness mean? So say we had a number. Does everyone have this written down if they want it? OK, so say we have a number. Say our number is like 0x 1, 2, 3, 4, 5, 6, 7, 8. So we've got this 4-byte number, 1, 2, 3, 4 bytes. And we're going to store it in memory. And we want to know the difference between what it looks like in little endian and big endian. So in little endian, it's the least significant bits that are stored first in memory. So in memory, this is actually going to show up as the 7, 8, and then the 5, 6, and then the 3, 4, and then the 1, 2. And if you don't know that's happening, you'll get confused because you'll read this off as the number 7, 8, 5, 6, 3, 4, 1, 2, and that's not the same as this. In big endian, we store the most significant bit first in memory, and it reads off the way we normally would. However, the Intel systems that we'll be using, that are used everywhere pretty much, do it this way. So in BombLab, you will have to worry about this and make sure that you are not accidentally interpreting it as a big endian number when it's little endian. So let's see, I think big endian is used by ARM. So if you're playing with your cell phone at the bit level, you'll get to see this, which is a little bit easier to read based on what we're used to. OK, so does that make sense, little endian versus big endian? And you'll see that again very shortly in BombLab. Everyone's good? OK. So then another thing we have to talk about is floating point. So floating point numbers are quite a bit more complicated than just integers. Integers are great. Integers are they're discrete. They're easy to work with. We have bits that are discrete, so the translation between the two isn't too hard. Floating point numbers are a little bit more tricky because now what we want to be able to do is we want to be able to represent fractions in our systems. So how do we do that? So the main idea is that we have sort of a binary point. So this is like a decimal point, except for our numbers are binary, not decimal. And the bits to the left of this point, are your normal powers of 2, starting with 1 and going all the way up to 2 to the I, however many bits you have. And then the bits to the right of the point are then the negative powers of 2, so 1/2, 1/4, 1/8, all the way down to 1/2 to the negative j, however low you go. And then this pattern, represents just the sum of powers of 2. So just like before with our integers, where we had a sum of powers of 2, we have a sum of powers of 2 here. It's just that some of those powers of 2 are now negative. So there's a particular standard for floating point numbers that's used just about everywhere, and that's the IEEE standard. So there's 2 different main versions of this, the 32-bit version and the double precision 64-bit version. So those are what you would call floats and doubles in C. If you're using another language that has some sort of floating point type, it probably maps to one of those. So if you've used SML, the type real is actually just represented by a double precision floating point number, for those of you who've taken 150. So what are the difference between these two? So the difference between the two is just how many bits we have for each portion of the number. So the number is split into 3 different bits. So we've got 1 bit for the sign bit. This is the same as with the integers. If it's 0, the number is positive. If it's 1, the number is negative. And then we have, in the single precision, 8 bits for our exponent, in the double, 11 bits for our exponent, and then 23 versus 52 bits for the fractional component. So I'll talk about what that means shortly. But essentially what we're doing is we have some fractional component, and we're multiplying it by some exponent. It's like a scientific notation, if you're familiar with that. And then there's also another 80-bit standard that's not as standard because it's not used everywhere. It's just sort of an Intel-only thing that gives you even more precision than a double. But those aren't used too often. OK. So yeah, so it's sort of like a binary scientific notation, like a simplified version of it. And we'll go over what it really is in a moment. But you're essentially doing the sign bit times the fractional component times 2 to whatever the exponent is. So there's a couple other things in it. But here's an example. So you've got 3 exponent bits, 2 fraction bits, 1, 0, 0, 1, 0. And we'll get to it shortly. But first, we should talk about how these things actually are. So first, let's talk about there's 2 different types of floating point numbers. There's the normalized numbers and the denormalized numbers. And so we care about a couple different things. So we want to calculate a couple different values. So the first is m, which stands for mantissa. And this is going to be equal to 1 binary decimal point, whatever the contents of our frac section is. So back here, that frac, those frac bits, those go here, following a 1 and a binary decimal point. And then you've got e, which is going to be equal to the contents of the exponent bits minus a bias. And then we've got the sign bit, and this is a sign bit. And our floating point number is going to be equal to -1 to the s times m times 2 to the e. So this is the actual formula for calculating the value that a particular floating point number represents. So what is this bias? This bias is going to be 2 to the k minus 1, where k is the number of exponent bits we have. OK. So let's work out what that particular number represents. So we've got 1, 0, 0, 1, 0. And I said that k equals 3, so 3 exponent bits, 2 fraction bits. So if we look here, the first 3 bits are the exponent, and the next 2 are the fraction. And we don't have a sign bit here. So we've got 1, 0, 0, 1, 0. So this is the exponent. This is the frac. OK. So what are these values going to be? So what's m going to be? This one's easy. For this example. Yep, 1.10. In base 2. And this is equal to what? This is equal to 3/2 in base 10. So it's 1 plus 1/2, the first place on the right-hand side of the binary decimal point. These are increasing powers of 2. These are the negative powers of 2. And then we have e. So what's our exponent? Our exponent is 1, 0, or 1, 0, 0, which is equal to 4 in decimal. And what's our bias? Our bias is 2 to the k minus 1. So we've got 3 exponent bits. So k is 3, minus 1 is 2. So 2 to the 2 minus 1. So that's 4 minus 3 equals 1. So m is 3/2. E is 1. We don't have a sign bit. We're assuming all of these numbers are positive in this 5-bit system. So what's the value of our floating point number? It's 3/2 times 2 to the 1 equals 3. So with no sign bit, 3 exponent bits, 2 fraction bits, 1, 0, 0, 1, 0 is equal to the decimal number 3. Does that make sense how we got that? And sure enough, the slides agree with me that that's the answer. OK. So we have a different thing, too, though. So that was in bits and 3 and 2 decimal point. These are increasing powers of 2. These are the negative powers of 2. And then we have e. So what's our exponent? Our exponent is 1, 0, or 1, 0, 0, which is equal to 4 in decimal. And what's our bias? Our bias is 2 to the k minus 1. So we've got 3 exponent bits. So k is 3, minus 1 is 2. So 2 to the 2 minus 1. So that's 4 minus 3 equals 1. So m is 3/2, e is 1. We don't have a sign bit. We're assuming all of these numbers are positive in this 5-bit system. So what's the value of our floating point number? It's 3/2 times 2 to the 1 equals 3. So with no sign bit, 3 exponent bits, 2 fraction bits, 10010 is equal to the decimal number 3. Does that make sense how we got that? And sure enough, the slides agree with me that that's the answer. OK. So we have a different thing, too, though. So that was a normalized number. This is normalized. We also have what are called denormalized numbers. So these normalized numbers are great, but there's a couple problems with them. Can anyone point out one particular problem with representing numbers using this formula? There's one that's actually really important. So notice what we have here with m, this 1 point whatever's in here. So that means there's always a 1 somewhere in our number. What does that mean about the numbers that we would be able to represent if we only had this? Yeah, we don't have 0. And 0 is kind of an important number that we want, right? 0 is a great number to have. So there's a separate format for denormalized numbers. So denormalized. And so with denormalized, what we're going to do is we're going to say m is actually equal to 0 dot whatever is in the frac bit. And the exponent is going to be negative bias minus 1, or negative bias plus 1. And then we're going to have the same formula here to actually calculate the value of the number. So now we can actually represent 0. Now we can actually represent 0 because we have a number that would be all zeros, and that's going to be 0. OK. So we know that a number is denormalized when the exponent equals 0. OK? And we know that a number is normalized when the exponent is non-zero and something else. So we're going to have to reserve a couple bit patterns to represent some special cases. Because floating point numbers can do more than just normal numbers. They also have special cases for infinity, for negative infinity, and for values that aren't a number. So for instance, if we try doing something like square root of negative 1, or if we try doing infinity divided by infinity, or 0 divided by 0, there is no number that corresponds to that value. So there's a special case of floats that will map to something called not a number, which signals that there just is no value that we can assign to this expression. So what we have for the normalized is that it's when the exponent is non-zero, and also the frac part is not all zeros and not all ones. So then the normalized has this implied leading 1. What's the corresponding part for the denormalized? What would be the right-hand side of this table? I wrote it on the board here. It's that we have an implied leading 0. It's the difference. And then here, we've got exponent minus bias. Here we've got the other way of determining the exponent. The normalized are denser near the origin, and they get more spread out as we get farther apart. Because what we're doing is we have this constant amount of precision for the fractional part, but this bias, this exponent, every time we increase it by 1, we've gone up by a power of 2. So we've gone up by a power of 2, but have this constant amount of precision here. So what that means is they're actually getting more spread out as we go towards negative infinity and infinity. The denormalized numbers are going to be evenly spaced. That's one of the properties of them. And then the normalized numbers are bigger numbers. I think I got this wrong. It should be 1 minus bias. So yeah, so the normalized numbers are large numbers, large in either extreme, numbers of large magnitude, and the denormalized numbers are the ones close to 0. And so whenever you're doing conversions between ints and floats and stuff, assume that it's going to be a normalized number until you have reason to believe that it's not, because most of them are. There's more normalized than denormalized. OK, and then here's the special cases. So I was talking about some special cases. So if the exponent is all 1s, so all 1s would be 2 to the k minus 1, that whole exponent is 1s, then that's infinity. And so you can get infinity if you go above what can be represented by a finite number. So you can just keep adding numbers, and eventually once you get bigger than the biggest number it can represent, if you try adding more to that, it'll be infinity. If you try dividing by 0, division by 0 is infinity. If you divide a negative number by 0, that's negative infinity. If you divide a negative number by negative 0, that's positive infinity again. There is a negative 0. So 0 would be when all of the bits are 0. Negative 0 would be when the sign bit is 1 and the rest is 0. Negative infinity would be the same as infinity, but with a sign bit of 1. So all of the exponent bits are 1 and a sign bit of negative 1. And then we have not a number. So in infinity and negative infinity, all of the frac bits will be 0. If you ever have a case where you have the exponent is all 1s and the frac is something other than 0, then that represents not a number. And so not a number and infinity are two distinct things. Make sure that you remember that they're two distinct things. Infinity is overflow or unrepresentable because it's too big value. Not a number is something that there is in math. There wouldn't be a number that you could assign to this even if you had infinite precision. It's something indeterminate. Something's gone wrong. You've done an illegal operation of some sort, like trying to take the square root of negative 1. or something like infinity times 0, which is indeterminate. So another thing about floats. So floats, you have rounding rules. So imagine you have a bunch of data stored as floats, and you're going to, like, I don't know, round it up to ints before you do something to it. If you had a case where, or I shouldn't say as floats, just imagine, a statistical situation where you have a bunch of data and you're about to round it because you can't keep it at the full precision. If you have a bunch of stuff that ends in 1/2, and you have a rule that's either always round 1/2 up or always truncate or whatever it is, then you'll have statistical bias because all of the 1/2s will go the same direction and you'll push your average either up or down from what it really should be. So there's a different way of rounding, a more statistically sound way of rounding, and this is what floats use so that as we lose precision, we maintain some sort of, we don't have that bias as much as possible, and it's called round to even. So what it is when you have a number and you have to round it, and it's straight in between two other numbers, it's like halfway between them, you round to the one that's even. So if we have, say, 1.5, and we want to round this to a whole number, by round to even, what do we do? 2, right, because 2 is even. Let's say we had, though, 2.5, and we're going to round it, and we're going to use round to even. What do we get? 2 again, right. So even though if you had the, the more standard rule of 0.5 just rounds up, this would round to 3. But with round to even, you round to whichever side is even. And this is a good rounding scheme. And so you see here, in the normal cases, where you're not exactly halfway between something, you do what you would expect. If you're below halfway between, you round down. If you're above halfway between, you round up. But when you're exactly in between, you'll round towards whichever number is even. Okay. So how do we actually implement that? There's some rules. So you can look at the part that's right on the boundary where it's going to be rounded. So you've got the last bit that's not rounded, the first bit that's going to be rounded away, and then everything below it. And so you take the OR of all of those bits, 2 to the end below what's going to be rounded, and you take the bit right below what's going to be rounded and the bit that's going to be the least significant bit once you do the rounding. And if you have 2 or more of them as 1s, then you'll be rounding up. Otherwise, you won't. You'll be rounding down. So there's the table there. OK. And so then we've got some examples here, just to finish off the recitation. So we're back to this 5-bit system, 3 exponent bits, 2 fraction bits. What's the bias? So I already calculated that before. So we had k equals 3, so that's 2 to the 2 is 4 minus 1, so the bias is 3. And then we can talk about, what's the largest denormalized number that we can represent? Since we're running short on time, we'll put the answers up and we'll just look at them. So the largest denormalized number we could represent, the denormalized number is here, where the exponent bits are all 0, so the first 3 bits have to all be 0. And then to get as big as possible, we could have all the rest of the bits be 1. And so that gets us to 3/16 when we apply this formula. The smallest normalized number we could represent would be where this part is 0 and we have the smallest fraction possible. That's going to be 1/4. The largest finite number we can represent is going to be 14. The smallest non-zero number we can represent is going to be 1/16. So what happens if we have this system and we try doing 14 plus 14? What is the resulting floating point number going to be? Yeah, positive infinity, right. So anytime we go over what's the largest finite number we can represent, then it just overflows into infinity. So here we have an additional table of practice problems. These are good ones for you to try out, but we're almost out of time. So I'm just going to put up the answers real quick. You should try these out and make sure that you understand why all of these work as they do. It's the same formulas we applied here, just working them out on different numbers, going different directions with them. So here you can see that 19, if we try representing 19, there's a case that's bigger than the largest positive number we can represent. We'll get infinity. OK, so here's a recap of what we talked about. Same stuff I wrote on the board. Formula for floating points. Most significant bit is the sign bit. The bias normalizes when the exponent is not all 0s or not all 1s. Denormalizes when the exponent is all 0s. If the exponent is all 1s, that's one of the special cases. Normalized, we've got 1 point frac and exponent minus bias. Denormalized, we've got 0 point frac and bias plus 1, or negative bias plus 1. And then here are the special cases. You've got plus and minus infinity, not in numbers. And you've got positive and negative 0. Always round towards 0. So any questions? We're out of time. Yes?
Style on this assignment. I know that shifting by a negative value is undefined behavior.
Right.
But if we have code that works correctly and passes that has a potential to shift by a negative value, but it doesn't affect it because on Intel doing that leads to a 0, is that all right? Can we submit that as long as BDD check says, or not BDD check, BDD check and writer.pl say it's okay?
So there's some assumptions that you can make about the behavior of the machine written in the bits.c file. But beyond that, what the BDD check does is, what it does. The BDD check is actually a symbolic execution. It doesn't actually run the code and execute it. So if what it's doing is passing, then you can use that. Yeah. Any other questions?
I'm gonna leave it there for tonight. Get some sleep. Go to the gym in the morning, and I will be back on tomorrow morning to get into floating points, getting through the reading, some of the problems, the practice problems, and then wrapping up chapter 2. I'll probably review the homework section to see if there's anything interesting in the homework that I might want to do. But I'm not going to go crazy on this chapter because I want to get on to next section, which is machine level programming 1 basics, which is, I think, assembly stuff. So I want to get there as soon as possible.